Alright, so we're looking at DC circuits, okay, and from the word DC, circuits, you realize that we have an acronym DC here, and of course this DC means direct current. Alright, this DC means direct current. We also have AC, but we are not looking at AC. We have AC, which is called alternating current, but here, like I said, we are not looking at AC, we are looking at just DC. Alright, so basically when we look at direct current circuits, okay, direct current circuits, put down, direct current circuits are circuits which allows the direct flow of electric current through the various components of the circuit. So they allow direct flow of electric current through the various components of the circuit. Okay, so they are circuits that allow the direct flow of electric current through the various components of the circuit. There are various definitions of DC circuits, but in this context, we are looking at circuits, I repeat, that allow the direct flow of electric current through the components of the circuit. Okay, and one thing you need to understand is that we have different components of the circuit. All right, of course, we have the battery, we have the switch. Okay, an electric circuit can also have a resistor in it. It can have some measuring devices connected, like voltmeter, ammeter, potentiometer, etc. All right, but when we look at DC circuits, the major component that facilitates the action of every DC circuit is known as a resistor. It's known as a resistor. It's known as a resistor. Therefore, we'll be looking at the concept. We'll be looking at the concept of resistance. We'll be looking at the concept of resistance. We'll be looking at the concept of resistance in this context. Alright? So, basically, when we look at resistance, the law that binds resistance in a circuit is known as what? Ohm's law. It's known as Ohm's law. Alright? So that's the law that binds the action, or that binds the resistance of a particular material in a circuit. Alright? So now let's look at the Ohm's law of electricity, or of electrostatics. Take down rather. Now please take down. Ohm's law states that the current flowing through a metallic conductor, is directly proportional to the potential difference across its ends. ENDS, that's what I mean by ends. So the current flowing through a metallic conductor is directly proportional to its potential difference across its ends, or is directly proportional to the potential difference across its ends. So what we are saying in essence is this, that the current I flowing through a metallic conductor, for current to flow in a circuit, there must be a conductor in that circuit. And what is a conductor? A conductor is a material that conducts electricity, or a conductor is a material that allows the flow of electrons through it. We have another form of material we call insulator. An insulator is a material that do not allow the flow of electric current through it. Okay, a semiconductor is in between a conductor and an insulator. So a semiconductor can conduct electricity, but when it has been doped with impurities, this is advanced electrostatics, or it's also under electronics, basic electronics. Alright? So that's not the point we are trying to make here. The point of emphasis is that the material that must be in the circuit to enable current to flow through it should be a what? Conductor. Should be a conductor. So we are saying that the current flowing through a metallic conductor is directly proportional to the potential what? Difference. So I directly proportional to V. So what it implies is that the I increases, V also increases. When I drops, V what? Drops as well. Okay? That's direct proportionality. Now, another thing we must lay emphasis on is the equation that depicts the Ohm's law of electricity. Now, this direct proportionality, okay, is basically explained in the formula V equal to IR. Alright, so basically, the formula that explains Ohm's law is V equal to what? IR. Now, from this formula, we can define it to be that, okay, the voltage is equal to the product of the current and the resistance. Okay, the voltage is equal to the what? Product of the current and the what? Resistance. I and R. Okay, so V is equal to IR, where V is equal to potential difference, where V is equal to potential difference, I is equal to current. Now your potential difference is in volts. I is equal to current in amps. Okay, in amps. This amps is what we call amperes. Alright? Or let me just write it in full, amperes. Okay? Then we also have R. R is the resistance. R is the resistance. R is resistance. Alright? In ohms. In ohms. Alright? Have you written this? Alright, beautiful. So R is resistance in ohms. Now paragraph. Resistance is described as the property. Resistance is described as the property of a resistor. As the property of a resistor to control or moderate the flow of electric current in a circuit. It's the property of a resistor to control or moderate the flow of electric current in a circuit. Alright? The flow of electric current in a circuit. So like I said, it is that property, it is that feature of a resistor. In fact, basically, it is the only feature of a resistor, because that's the only function of a resistor. When it is placed in a circuit, what happens is that it controls the flow of electric current. It moderates the flow of electric current. Okay? When we say in an occasion we have a moderator, what will that moderator be doing? The moderator will be ensuring that time is being kept. The moderator will ensure that anyone who mounts the podium or anyone who mounts the stage to do one or two things must be the person assigned to do that thing. Somebody who is in control is someone who must ensure that the affairs of a particular thing are properly met to ensure productivity. So on a norm, the current in a circuit is supposed to be increasing. It's supposed to be growing above its height. It's supposed to be flowing more rapidly than it is supposed to. But then, here comes the resistor to say no. You have to limit the rate at which you flow in the circuit. Because by the time currents do not have anything to control it, the circuit will break down. That's why you realize things like sparks. It don't sparkle, it don't spoil. You buy a new charger, it don't spoil. Say, what did they happen? Maybe the resistor in that particular circuit is bad. Or maybe the capacitor has not been able to store enough charge that is required of it to stop, or there can also be other reasons for that. But resistors can actually play a very huge role in the amount of current that flows in the circuit. Are we together? So that's the major point. Okay, that's the major point. So we say resistance is that the property of a resistor to control or moderate the flow of electric current in the circuit. That is what resistance is. Okay, now the device that enables resistance to be possible is called the resistor. Okay, so the device that enables resistance to be possible in a circuit is resistor, is the resistor. Is the resistor. Alright? Full stop. Now right. In every given circuit, resistors can be connected in two different forms. In every given circuit, resistors can be connected in two different forms. Number one is what we call the series connection, and number two is what we call the parallel connection. Number one is what we call the series connection, and number two is what we call the parallel connection. We are going to be looking at these two different ways of connecting resistors in a circuit and look at how they actually apply to the overall development of DC circuits. Okay? So now let us begin with series connection. Like I said, there are two ways. We have the series connection and we have the parallel connection. Let's look at the series connection first. Okay? So now, for series connection, take down. Series connection. Now, resistors connected in series, okay, have the same current or have the same amount of current flowing through them, but different voltages. Resistors connected in series have the same amount of current flowing through them, but different voltages. Alright? So basically what we are saying is that if you connect 3 or 4 resistors in a circuit, okay, those 3 or 4 resistors would have the same amount of current. Amount of what? Current. But will have different voltages. Alright, full stop. Now the circuit setup of the series connection, is indicated as follows. The circuit setup of the series connection is indicated as follows. So this is the circuit setup. Alright. Now this symbol is what indicates resistance. Sometimes you can also see this. Alright. You can also see this. This can also indicate resistance. Alright. Either this or this. Now, mind you, sometimes you see something like this, but it is not it. Sometimes you see something like this. This is what? Inductance. Alright, this is inductance. So don't mistake one for the other. Alright? So now of course we can have a switch like this. Okay? Then we have a battery. Alright, we have a battery connected at this point. Okay? Then we can have a voltmeter. Then here we can have an ammeter which goes up. Maybe the switch will be open like this. Alright? And of course this is a wire. Let's say current is flowing in this direction. Alright? So we can call this R1, call this R2, and call this our R3. Okay? So the general idea is that for you to know that resistors are connected in series, you have just one wire. Nothing is demarcating them. There's no form of demarcation. Nothing is separating them. Alright? So you have just wire, and of course the different resistors are connected in what? This one wire. Alright? Is that okay? So basically, when we have this circuit, we are saying that it is the same current. It's the same current. Let's say that the battery has a voltage of 50 volts. It's the same current but different voltages. Different voltages. So what we are implying in essence is that you see this 50 volts. These three different resistors will share the battery. Are we together? These three different resistors will share these 50 volts to ensure that they limit, control, or moderate the flow of current in the circuit. Alright? So what we are saying in essence here is that in a circuit that has resistors connected in series, our I1 is equal to I2, I2 is equal to I3, and all of them are equal to I. All of them are equal to I. Your I1 is the same as your I2. I2 is the same as your I3. I3 is the same as your, of course, general I. Alright? But your V1 may not be equal to your V2. Your V2 may not be equal to your V3. Alright? So V1 is not even a matter of may, it will not. V1 is not equal to V2. Neither is V2 equal to what? V3. They have different voltages when you have a series connection. But if you want to determine a particular parameter here that is unknown, you must refer back to the formula that V is equals to IR. It's very important, okay, that you must refer back to the formula that your V is equal to the product of your I and your R, your current and your resistance. Okay, so now let us imply and present what we have already said here. Okay, now looking at V equals to IR, what we are saying here is that if we want to look for V1, knowing that in a circuit that resistors are connected in series, if we want to look for V1, for instance now, alright, so the reason why we have just I here is because, of course, the I is just one in the circuit, alright? So we don't have different current flowing through the circuit. We have just one current flowing through the circuit, alright? So of course then V2 now will be IR2, V3 will be IR3, alright? So this is the concept, this is the idea of the whole looking for voltage in a series connection. Now let's look at parallel connection. Take down. Now resistors connected in parallel have the same voltage but limits different amounts of current. So if you look at it very well, you realize that it's the direct opposite of resistors in series. Okay, so okay, full stop. All right, it is indicated as follows. So this is the circuit, this is how it is. Alright, so you have the switch here. Alright, then coming down, maybe you have an ammeter here and a voltmeter at this point. Then here you have another wire that connects to this point. Okay, you have another wire that connects to this point with another, let's call this R1, let's call this R2. Then here as well, you have another wire that connects to this point. Let's call this R3. Okay, then here we can have a battery. All right, let's say that it is 50 volts as well. Now if you look at the way this is assembled, you agree with me that these are different wires compared to the one in series that you had just one straight wire containing the different resistors. All right, so one thing you need to understand is that you see this guy here, this 50 volts, all of them are 50 volts. R1 has a battery of 50 volts. R2 has a battery of 50 volts. R3 has a battery of 50 volts. Now that doesn't mean that you add them. No. It doesn't mean that in this circuit you have 150 volts. No. They are using it independently. Okay? R1 is not depending on R2 for voltage. Neither is R2 depending on R3 for voltage. You are not summing all of them together. Alright? So the total voltage in a parallel connection where you have resistors is not the sum of the voltages used by the different resistors. No, it is not. Alright? It is just basically identifying that the general voltage here is used by each of them in the same proportion. The same proportion. Okay? So, understanding that, you agree with me that just like we had series, that the one that you have to look for is V1, knowing that there are different voltages. Here you have different what? Currents as well. So you know that V is equals to IR, right? So it means that I will be equals to V over R. So if you want to look for I1 will be V over R1. Why did you not say V1 over R1? Because we have the same what? Voltage. Now I2 will be V over R2, while I3 will be V over R3. So the idea is that your I1, okay, is not equal to I2. Neither is I2 equal to I3. They are not equal. But your V1 is equals to V2, and it's equals to V3, and they are all equal to V. They are all equal to V. Not V1 plus V2 plus V3. Remember, you don't add them. Okay, it's not the sum. Alright. So basically, this is the concept of series and parallel connection when it comes to resistors. The next thing we'll be looking at now is equivalence in bracket total resistance. Equivalence in bracket total resistance. Okay? So we'll be looking at equivalence in bracket total resistance. Now what you need to understand is that in both the series connection and the parallel connection, we have total resistance. And they differ from one to the other. Alright? So for series connection, how can you get the total resistance in the circuit? It's very simple. When you have total, it means addition, right? Total means addition. So it means that your R equivalent, R eq, will be equals to R1 plus R2 plus R3 plus Rn. Why I put these ellipses? These dots, 3 dots, they are called ellipses. Ellipses. Why I put that ellipsis is because there can be many more. Look at Rn here. You can have up to 100 resistors connected in one circuit. You can have. Yeah. Alright? So this is for series connection. Now if we have parallel connection, it's a different ball game. Okay? Now if we have parallel connection, to get the equivalent resistance, okay, is different, but it's not difficult. Alright, different, but it's not difficult. So parallel connection, we have 1 all over Req will now be equals to 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over Rn. Now, the mistake a lot of students make is that by the time they have added these guys, they'll just say that's the answer. For instance, you have R1 to be 5 ohms, R2 to be 3 ohms, R3 to be 1 ohm. When you've added 5, 1 over 5 plus 1 over 3 plus 1 over 2 or whatever the resistance is, you just add like this and you write your answer. Wrong. If, for instance, you solve this and your answer is equal to, for instance, so you have 580, 1 over Req, and this is equal to 5, you can never say that this is your answer. The reason why you can't do that is because you have not made Req subject to the formula. Unlike series that Req is just R1 plus R2 plus R3. It's not like that here. So you can't just get to this point and say, wow, I've achieved it in life. No. You cannot do that. Alright? Rather, what you will do is that when you get to this point, okay, you now have to cross multiply and you take the inverse of 580. That will be your answer. 1/580. That is after you have added these guys and you get this. Still look for the inverse. Are we clear? Let's look at our first example. Guys. So don't forget, this for series, this for parallel. Take down. Number 1. Now determine the amount of current. Determine the amount of current flowing through a circuit with a potential difference of 5 kilovolts. The potential difference of 5 kilovolts and a resistance of 980 ohms. Determine the amount of current flowing through a circuit with a potential difference of 5 kilovolts and a resistance of 980 ohms. Okay, so this is of course a very simple exercise. Okay, now we need to understand our foundation of Ohm's law. V equals to IR. Now solution to this is that we have voltage of 5 kilovolts, we have current which is unknown, our resistance is 980 ohms. Now listen, kV is not a unit. The unit for voltage is what? Volts. Don't ignore this guy. Don't ignore K. Don't marry it together with V. No, don't do that. 5 kilovolts means 5,000 volts. Kilo is 1,000. In fact, in our usual pidgin English, we say 2K. 2K is 2,000, right? But that K means kilo. 2 kilo naira. That's what it means literally. After, borrow me like 50K. What you're implying is, borrow me like 50 kilo naira, man. You get the point now? So it is kilo. So 5,000 volts is of course the voltage that we have. Ensure you convert to express it in volts. Now we are looking for I. So I will be equals to V over R, which will be 5,000 volts. 5,000 volts divided by 980 watts ohms. Are we getting it? So 5,000 divided by 980 will give us what? 5 point what? So we have 5.102 amps. Capital letter A. That is our answer. Straight up. No, you cannot determine from the question because they do not state that resistors are connected in series or parallel. Okay? You must actually have a question that will state that resistors are connected, or you'll be given the diagram. But this one is just one resistor. And you are told to look for the current that is flowing through the circuit where that resistor is. Let's look at the second example. Take down. Now, how much potential difference is present in a given circuit containing three resistors in series, with resistance of 4.5 kilo ohms, 2.5 kilo ohms, and 1.5 kilo ohms respectively. 4.5 kilo ohms, 2.5 kilo ohms, and 1.5 kilo ohms respectively. Alright, respectively. Comma, if the current flowing through the circuit is 1.25 milliamps. If the current flowing through the circuit is 1.25 milliamps. Full stop. Alright? So let's provide solution to this question. Now, we are given 3 resistors. Okay? And these 3 resistors are connected in series, right? Now, it's exactly like this. Okay? Then we have a voltage. We have a voltage of what we don't know. Alright? But we have 3 resistors, 4.5 kilo ohms. We have 2.5 kilo ohms. And we have 1.5 kilo ohms. Then the current that is flowing through this circuit, we are being told that is 1.25 milliamps of current. When you see that arrow, it indicates current flowing. Now we are told that we should look for the voltage. The total voltage that is here, what does this volts here represent? That is the battery, what does it represent? What voltage is in this circuit? Now, I told you that when you connect resistors in series, you don't have the same voltage. Rather, what do you have? The same current. And we are saying that all the different voltages for the different resistors sums up to give you the general voltage. So what we are saying is that if you have a general voltage, all the resistors takes potential difference from that battery to resist the flow of current. It's very important. It's sacrosanct for you to understand and distinguish this appropriately. Now, we are looking for the voltage, general voltage, but we need to first of all know the voltages that each of these resistors are using. It's when we know the voltage that each of these resistors are using that we will now add all of them together and we'll get the general voltage. Is that correct? Is that what we're supposed to do? Alright. Now, we know that in this particular circuit, our voltage is not the same across all resistors. We remember that V is equal to IR, right? So we need to look for V1, V2, and V3. Alright? So V1 is equals to, okay, I1 what? Or IR1 rather, right? Because there's no I1, it's the same current. So V1 will be equal to 1.25 milliamps times 10 raised to power minus 3. That's what milli means. Then times your R1 is 4.5 kilo, which is, let's say, 4,500. Am I correct? Beautiful. Is that correct? So when we multiply this to what will we get? Do that quickly. Okay, I just don't want to be doing that very fast. 1.25 times 10 raised to power minus 3 times 4,500. What do we have? 6.75. Any exponent? No, 6.75 volts. Now V2 is equal to still the same current, 1.25, but of course let me state it that V2 will be equal to IR2. So this will still be 1.25 times 10 raised to power minus 3. Then times R2 is 2.5 times 10 raised to power 3, which is 2,500. Okay? So this is what? Alright, please let's make that correction. 5.625. Okay, 5.625. Alright. Okay. Now when we multiply this by 2,500, what are we going to get? 3.125. Is this one correct? Because I'm not having calculator with me here, so you are my calculator. 3.125 volt. Now V3 will be equals to IR3. Our I is 1.25 times 10 raised to power minus 3 times R3 is 1,500, which is 1.5 kilojoules. So when we multiply by 1,500, what are we going to get? 1.8 what? 75 volts. Okay? So when we add V1 plus V2 plus V3, okay, so it will have 5.625 plus 3.125, then plus 1.875. What would this summation give us? Confirm that. So we have 10.625 volts. So this is our V. Alright? So V1 plus V2 plus V3 is equal to V. So it means that this is the general voltage that is used in this circuit. So this guy is 10 let's just say 10.6 volts. So this is what is used as the voltage in this circuit.